right, we can see that. Good morning, everybody. I'm Ayman, and along with my colleague Howard, we'll present an ongoing appraisal of natalizumab biosimilar and its originator for a subpopulation in MS. And we're making the presentation on behalf of the Bristol Evidence Synthesis Group, or sorry, the Technology Appraisal Group. Yeah. So I'm just going to give a brief outline of the talk and then give you an overview of the project and tell you about the model and give some concluding remarks, and it'll be a very quick presentation. NICE, all of you familiar with NICE, their position statement on appraising a biosimilar is that they would do it along with an originator in an MTA when the originator is not licensed for an indication. So in this case, natalizumab is licensed for this subpopulation of relapse remitting multiple sclerosis for patients at first line, but not at second line. So these highly active patients, they're having one relapse in the previous year, and there has to be MRI evidence of disease activity despite treatment. So they're sort of treatment resistant. And so when we started out the project, we had over 14 therapies that we were modeling, and then as it went along, it became apparent that clinicians preferred the treatments that are in bold. These are the newer treatments, and so you can see as well that there are classes of treatments there. So when treatment effects were missing, we were able to borrow across treatment classes. So we did a pragmatic search, and we just focused on RMS models that have been used for decision-making in the UK. Most of them, all of them are this 21 health state Markov model, and it's a disease, it just moves according to the disease severity, which is measured on an ordinal scale. It's called the Expanded Severity and Disability Scale. I'll just refer to it as EDSS. Relapse remitting patients can move up and down the scale, and they can move to secondary progressive MS, and they can move to death at any of these nodes. And this is a typical model that's been used in all of the appraisals before, and in Excel as well. So the key issues with this type of model is treatment sequencing and variable treatment waning was an issue. In clinical practice, patients switch to alternative treatments if their drug is no longer effective, but this was never modeled. All of these appraisals use a pretty old data set for relative risk of death, and it's a data set that came from an insurance just not a very scientific publication. And they all had the limited ability to reflect accurately the natural history of disease. So some models produced implausible numbers of patients in high severity states, and they had issues converting patients from one type of disease to the other, from relapse remitting to secondary progressive. So our model is influenced by the recent Dutch clinical guidelines model, which was a microsimulation accounting for treatment sequences. However, they didn't run a DES, they ran a microsimulation using an underlying multi-state structure, also defined by EDSS, RMS, and SPMS status. This is similar to Markov models used in previous NICE submissions. And so the point here is that cohort models require a large number of health states and tunnel states. And here's an example given in atrial fibrillation of a quite a bushy model that was used to inform clinical guidance for NICE. And we gave our justification for adopting an event-based rather than state-based models that we wanted to target RMS treatment to reduce events of relapse and disability progression rather than directly modeling the health states themselves. And we thought the DES would be better suited to incorporate RCD data. Right. This is the model. So the attributes of the DES represent important demographic and disease characteristics. The model disease characteristics include EDSS severity states from 0 to 9 and SPMS status, and thus captures the health state information that you would find in a typical RMS Markov model. Age and gender were modeled as demographic attributes and determined the rate of background mortality. Treatment status was also included. The event rates in the second box depend on some of these attributes. Giving an example here is a flag for secondary progressive MS. So if patients have not progressed, then events include severity increases and decreases, and progression to SPMS, relapses, adverse events, and treatment change, that's the switching part, and death. If patients progress to SPMS, then it's just limited to severity increase and decrease and just adverse events and death. Competing risks are resolved using event-specific approach, which requires sampling times from competing events and simulating the event that occurs first. Sorry, I haven't provided any mathematical equations, but I hope this is... The initial treatment sequence, so we started second line because these patients have already been treated with a DMT, and it follows the distribution of patients on the UK MS registry that we used for the natural history. Following this, there's rescue therapy and later line therapy at third and fourth lines, and these are just the competitors that are available, and that's just randomly assigned. And SPMS patients are assumed to receive an average basket of approved therapies. So we've used the registry data to model the natural history of this population, and this population matches the ones that were used for the NMA, namely the highly active relapse remitting multiple sclerosis, and who have received at least one DMT. And we did a second backup population, so just all of the RMS patients. Rates obtained by fitting exponential survival models. We didn't need to fit anything else other than exponential. I think we tried multi-state models that didn't converge. So that's probably due to missing data, and we had covariates on treatment and on the EDSS severity state. And EDSS is just a very wide term. There are lots of sort of questionnaires out there that are called EDSS. So the covariates of the treatment are only applied to obtain baseline rates on natalizumab, and then we apply the hazard ratios from the NMA to the baseline rates. This was one of the key criticisms, mortality, so we adopted a pragmatic approach to modeling all-cause mortality from MS patients. The average standardized mortality ratio across EDSS levels matched a publication by Jake et al., and differences between EDSS categories matched to Harding et al. And so Jake et al. Is a study informed by a cohort of MS patients diagnosed between 1993 and 2006 from the UK General Practice Research Database. I gave a robust estimate of 1.68. I'm not showing the uncertainty in the data over here. And the study by Harding is informed by a cohort of patients from the Southwest Wales MS registry, and it's estimated by EDSS, so stratified SMR. And so we've sort of combined the data from Harding and Jake. It's the data from Harding, and it's been centered around 0, and then you've added the SMR from Jake on as a, just centered on there, as assuming that it's the average, and then sort of rescaled the whole thing. Briefly showing NMA slides for illustration purposes. These were undertaken in Bayesian framework with multi-NMA, and just over here, that's a network plot, that's a forest plot, and just showing you that the reference treatment, natalizumab, the vertical line over here. So any hazard ratio that's greater than 1 is worse. Any hazard ratio less than 1 is better. And you can see there's a very high degree of uncertainty in the data, and across 1. Right, and these are the rest of the outcomes. Health-related quality of life. The utilities are associated with disease attributes and stratified by disease severity. Utilities are from a UK MS survey, 2005. It's a postal survey, so you can criticize it if you want, but it's been used in all of the MS appraisals. It's linear regression, it has moderate explanatory power, and we've used scenarios with trial utilities, but there aren't any, there's not a lot of information out there. And we have the standard adverse events and care utilities in there. Cost, I'm presenting here the public prices version, so costs aligned to the BNF. Treatment administration costs are basically outpatient day cases, and all of this has been stratified by EDSS state and been verified by our clinicians. I'm not showing any code here because I think it's very long, but we've set it up in DESM, which is now Warden, and we're going to adapt it at some point. So I'll quickly run you through it, and at some point we're going to publish code, so you're going to be able to see this. We set up treatments on second line and third line, and then we import all the data, and all the data are in other scripts. And then we set up first the common patient inputs. These will be depending on whether you choose to run the model deterministically or probabilistically, so just a bunch of matrices with covariates on age or disease severity, and these are for the baseline characteristics and natural history, treatment effects, mortality, costs, and utilities. Then there are flags for unique patient inputs. They track the age, the sex, the disease type, whether patient has progressed, their death, the number of events. That's for validation purposes. And time spent on treatment and severity states. You set up the initial events. Those are rates and with coefficients from the NMA if you're applying these treatment events. And there are reactions to the events, there's discounting, and then you set up the simulations. And so you have a simulation model that allows you to estimate average time patients spent on treatment, so that's great for validation. You can estimate the average time in severity states, which is more reflective of a modern cohort where patients spend the majority of their time on lower severity states that are not touching 7, 8, or 9. This is mortality, and so this is like a Kaplan-Meier plot without the censoring. So you just have number of events and survival, and you can see that there's median survival at around a little over 40 years, and no difference between the treatments. Standard ICERs. I've deleted the treatment names just because this is ongoing, but these are public prices. They're uncertain, so we advise not to go with ICERs, prefer to go with incremental net benefits. And but these are less familiar to decision makers. They're kind of uncomfortable using them. And you get the Bayesian cost effectiveness analysis outputs over here, what you normally would see. And quickly, so I think DESM or Warden is a rapid way for building a DES model. And so I encourage all of you to try it. Workflow in R is great because it integrates with other teams like stats, and you can also collaborate on GitHub. It's transparent and well received by committee members who know how to use R. The cons, it's computationally intensive. You need to run it on a high performance computer. It's inaccessible to R users, and because it's already modularized, so it's difficult to further modularize this. So you have a really long script to run. Yeah. And thank you. Questions?
So are there any questions in the room? Oh, yes.
Thank you very much for the presentation. Was it a company who approached the submission with a discrete event simulation, or was it the EAG?
It was the EAG. Howard wanted us to build them, to knock them off their feet, so we did. Yeah, they submitted a cost comparison. They just wanted to go with a cost comparison, so they didn't even submit a model, and I think we kind of put them on the spot.
Sorry.
Thanks. Javier here. I'm the one who developed DSM and Warden. So I was curious about what feature do you think was missing the most, or you would like to have in order to make, the programming easier, or like the modularization that you were mentioning, right?
Yeah, the modularization, that would be helpful. I mean, I haven't looked under the hood, but maybe Howard could say something, because you wrote some code to extract the input matrix, and you wrote a few functions.
Yeah, there were just some distributions we were adding, so we can tell you which ones we added. But mostly the modularization was the mess, that we couldn't split it up into separate files because of the way you'd use pipes. So it'd be really interesting if you could change that.
Thanks.
And maybe one more question?
Thank you. Just maybe a minor point on the computationally intensive machinery. Sometimes that's needed, and that's all we have. The other point is there any way that maybe even more efficient software can be employed? Like, we know that R is our choice, and we make a big spiel, obviously, but is there a possibility of expanding this framework to something that is even more efficient, which sometimes other languages can be?
Howard?
Well, that might be a question for Javier.
We all are about R, of course, but again, the bigger point, R-HTA is kind of a proxy for proper statistical software for HTA.
Yeah. Sorry for hijacking. Just very quickly, yes, there are. In fact, there is the micro-simulation package which uses C++. But, it's a challenge because then you need to know C++.
And if you guys are interested, we have a modeling group at Bristol. You can email either Howard or myself. We're going to give a longer presentation on this, probably show some code and things. Yeah. Thank you.
So thank you very much, Ayman.